Hello everyone to our 380 presentation. Today we're gonna discuss the topics of soldering, brazing, and adhesive bonding, and we're gonna specifically focus on the techniques and the applications of each one of these. This presentation was done by Juan, Haley, Cameron, Maxime, and Reed. And as a group, we meet every week to put together this presentation, so hope you guys learn something new with our exposition. So the order that we are gonna follow in this presentation is the following. We're gonna start with soldering by giving you guys an explanation step by step of the process of this one, the different types that exist in the market nowadays, the applications that soldering uses in the different industries, and the advantages and disadvantages of this method. After that, we're gonna follow with brazing. They're gonna give you a barely introduction of the theory, so all the conceptual part of this method. They're gonna give you as well the step-by-step of this method and the applications that they use nowadays of this one. Finally, we're gonna follow the topic of adhesive bonding. So they are gonna explain you as well the step-by-step of this one, the different types that they exist, the applications, and finally, we give you some advantages and disadvantages of using this method over the other ones.
Soldering is the process of joining two or more metal components together by melting a filler metal, called solder, into the joint. The solder cools and hardens, creating a solid electrical and mechanical connection. A good solder will have a shiny and smooth finish, which indicates proper heating. The joint should not move during cooling because this can create cold joints. There should be a proper amount of solder on the part so that the part is not weak or brittle. A joint should also not be burnt or overheated. This will result in losing flux. In the next few slides, I will be going over the process, the types of soldering, tools and materials, and applications. Cleaning is required for both the joint and the solder iron before soldering. The iron can be cleaned with a damp sponge in order to remove any residue. The joint can be cleaned mechanically or chemically. The next step is to flux the joint so that the metal will be less prone to oxidation. After this, the joint is heated so that the solder will flow properly, ensure a proper bond, and in order to avoid a cold solder. The solder is then placed on the joint where the solder needs to be made. The part then needs to be cooled naturally. And so here we have a little video of the soldering process. As you can see, the solder is being applied and the iron is there as well. There are three different types of soldering. The first is soft soldering. This is done between 194 degrees Fahrenheit to 842 degrees Fahrenheit. The filler used in this process has the lowest melting point at less than 752 degrees Fahrenheit. The filler metals are typically alloys. The joint this process produces are not the strongest joints, but they are used because the low temperatures do not thermally stress the components. This soldering technique must be done in this range because otherwise the metal will lose strength. Next, we have hard soldering. Hard soldering is also known as silver soldering and is done above 842 degrees Fahrenheit. Typically, brass and silver are used in this process. A blowtorch is also required for this method in order to properly heat the materials. Brazing is the third type of soldering, which will be discussed later in this presentation. The tools and materials used to solder are a soldering iron, solder, and flux. The soldering iron is a hand tool used to heat solder that is usually connected to an electrical supply. The electrical supply keeps the iron at temperatures above the melting point of the alloy, allowing the solder to flow between the workpieces being joined. There are many different types of solder, and it's important to use the right one for different applications. Some types of solder include plumbing solder, lead-based electrical solder, lead-free electrical solder, solid wire solder, rosin core solder, and many different thicknesses. Lead-based solder is easier to work with. However, lead-free solder is safer to use. Rosin core solder is better because it sticks to the flux more efficiently. The thickness depends on the scope of the project. Sometimes the part that is being soldered can have oil, dirt, or oxidation. The flux will help prevent oxidation and chemically clean the metal. The flux used is rosin flux, which helps with the mechanical strength and electrical contacts in the part. Soldering is very commonly used in fields like electrical, plumbing, jewelry making, sheet metal work, aerospace, automotive, and there's even micro soldering for electronics. As you can see here, there's an example of soldering being used in making jewelry, and on the bottom we have the micro soldering for electronics.
Now we're gonna discuss a couple of advantages and disadvantages that we can identify in soldering. The first one will be good conductivity. The soldering provides excellent electrical conductivity, ensuring an efficient current flow between the different components. So as we are using a metal and we melt that one in order to combine the different components, this will allow also the electricity to flow from one part to the other one. Of course, if it is not done properly, then you will not have this benefit. Versatility is the next one, used for a wide range of applications for its simple joining method. So you will see soldering in different amount of industries because it's easy steps to do. The next one is low cost and easy to use. Soldering materials are mostly inexpensive. It is a technique easy to teach and learn. This makes it a cost-effective solution for joining components. So let's imagine that you have a group of workers that you gotta teach them soldering. So if you teach every single one of the steps, they will learn it really fast because it is simple, and you will not take more than 2 hours or an hour, depending of course of the level of workers that you have with the skills. The first disadvantage is heat sensitivity. Since this process involves heat, it can damage those components that are heat sensitive. For example, in technology, we use a lot of sensible components that if you apply a lot of heat to them, it will damage right away that component. So a great example will be sensors. The next disadvantage is difficulty in disassembly. Disassembling solder joints often require additional heat, and it can be more complex than unscrewing or unbolting the connections. Since you are using a metal and you melt it, for combining and putting together the different components, you are required to also melt again that piece of metal that you add in order to put apart the different components. So the effort for doing this will be way higher than just providing or getting new material.
Brazing is a joining process, similar to soldering, in which a filler metal is melted and used to bond workpieces without melting the base material. Brazing is a higher temperature process than soldering, typically exceeding 450 degrees centigrade, and requires very clean surfaces to adhere to. It's typically used on dissimilar metals, but can also be used on similar metals or even non-metallic materials like ceramics and stones. Advantages to brazing include ability to join dissimilar metals, ability to be used on fragile base material that's very thin, or just in general heat sensitive. Lower heat effect on base material structure than welding, since you're not actually melting the material and inducing no residual stress. And it can be used to fill cavities, like those between pipes. Disadvantages include lower strength than a welded joint. It may not be suitable for environments with extremely high temperatures where the filler may melt, and it requires a special skill set. Brazing theory. Brazed joints are made possible by using a metal with a lower melting point than the base material. It's often a brass-based alloy containing copper or aluminum. The brazing filler melts and fills the surface imperfections on the base material. This creates a strong bond even when the filler solidifies. This is only possible with a very clean surface, since it must be free of any oil and debris. This exposes the microstructures on the surface, and the filler material can fill those gaps. Sometimes brazing flux is also required to be applied to the base material, which get rid of oxide layers when brazing, and that results in a stronger joint. Different base materials require compatible filler metals that liquefy and wet out the base material at the correct relative temperature. These brazed joints are strongest when within a specified clearance between the base materials. The gap is dependent upon the base material, filler material, and joint configuration, but typically falls between 1 and 10 thou. Brazing can come in many shapes and forms. Most common is torch brazing, in which an oxyacetylene or propane torch is used to heat the material, and then the filler is melted by touching it to the material. For mass production, furnace brazing is often used. This is where an oven is heated up to the temperature necessary, and a batch of parts is loaded in to the furnace, which already has preloaded filler in the joints. Induction brazing utilizes induced magnetic fields to generate heat in ferromagnetic parts, which can then be used to liquefy the filler metal, which has already been placed in the correct position. Resistance brazing is similar, just using electric current. TIG brazing resembles welding and uses a TIG welding torch in order to deposit the filler rod over a joint rather than inside it. This creates a joint that looks similar to a TIG weld, but in reality is brazed. Dip brazing utilizes a molten salt to melt the parts, which liquefies brazed filler metal that's already in the gaps. Infrared brazing uses heat lamps to supply radiant energy and melt the brazing filler. Common applications of brazing are plumbing and HVAC, where it's used extensively to connect high pressure refrigerant lines or other copper lines typically. Machine tools use brazing to connect dissimilar materials. For example, attaching a carbide cutting insert onto a steel tool holder, as shown in this image, using induction brazing. The medical industry uses furnace brazing to produce high precision parts, and jewelers can use brazing in order to join gemstones to other dissimilar metal materials.
I am Maxim, and I will be introducing adhesive bonding. Adhesive bonding is a technique used to join two or more materials using a substance that hardens to form a strong interface between surfaces. What makes it unique is that it typically occurs at lower temperatures compared to processes like welding or soldering, which means it doesn't alter the base material. Bond formation relies on various mechanisms such as mechanical interlocking, chemical bonding as covalent bonds, and physical adhesion through van der Waals forces. These allow adhesives to form reliable connections even between dissimilar materials. Adhesives are commonly grouped into three categories based on their behavior. Thermosetting adhesives, like epoxies, are rigid and heat resistant, ideal for aerospace or automotive panels. Thermoplastics, like hot melts, are flexible and reworkable. Elastomers, such as silicons and polyurethanes, are known for their flexibility and moisture resistance. When designing joints, shear loading is preferred, since it distributes stress evenly. In contrast, tension, cleavage, and peel loads concentrate stress and should be avoided when possible, as shown in the diagrams to the right. Now, let's talk about specific adhesive types and where they're used for. Epoxies are known for their high strength, chemical resistance, and temperature stability. They're used in structural applications like aerospace frames and automotive panels. Acrylics cure quickly and offer UV resistance, which is useful in plastic metal bonding. Cyanoacrylates, commonly known as superglue, provide instant bonds which are great for small parts and repairs. Silicons are flexible, waterproof, and heat resistant. They make it ideal for electronics or weather seal joints. Polyurethanes are versatile, durable, and flexible. They bond well to glass or construction materials. Applications spanning across industries include automotive for windshields, body panels, and vibration dampening joints, construction for sealing facades, flooring, glass sealing, and waterproofing membranes, electronics for bonding components, sensor sealings, and potting PCBs, medical for resin dental fillings and surgical adhesives, aerospace for lightweight bonded panels and insulation. I'll present the surface preparation and bonding process. The step-by-step process includes first cleaning, which you should use a 50-50 mix of isopropyl alcohol and water to remove oils, dust, and debris. For tougher contamination, a degreaser or solvent may be necessary. Number 2, abrasion. Lightly abrade the surface to remove oxidation and increase roughness for better adhesion. Always clean again afterward. Number 3, if needed, priming. Apply an adhesion promoter to hard-to-bond surfaces like low-energy plastics or painted metals to improve bonding. Number 4, adhesive application. Spread the adhesive evenly and ensure good surface contact. Apply pressure as recommended. And finally, number 5, curing. Follow the adhesive's curing instructions. Most adhesives reach full strength within 72 hours at room temperature.
Advantages of adhesive bonding. So the first one is the low temperature process, which is good for combining heat sensitive materials like plastics, composites, or electronics without distorting it. So unlike welding or brazing, adhesive bonding occurs at or near room temperature, which is really ideal for thermal sensitive components like plastics, thin metals, or electronic boards where the heat can end up warping, melting, or degrading the material. Number 2 is the ability to join dissimilar materials. So adhesives are very versatile when it comes to bonding different types of materials like metal to plastic, ceramic to glass, or composite to wood. And this is very useful in the automotive, aerospace, and electronics industries where hybrid materials are very common and the traditional joining methods like welding or brazing does not work. Number 3 is the even stress distribution, which adhesives distribute stress across the entire bond area, especially when it's in shear. This reduces the likelihood of failure at specific points, unlike rivets or screws that can create localized stress concentrations. And it is also one of the reasons adhesives are preferred when it comes to load-spreading joints, such as the bonded panels in our vehicles or planes. Number 4 is weight savings. So this eliminates the need for mechanical fasteners like bolts, rivets, or clips, which add a lot of weight. Especially important in industries like the aerospace and automotive, where every gram matters for fuel efficiency. This lightweight bond also helps in consumer electronics for more sleek and minimal designs. Number 5 is the sealing capability. So adhesives provide a very waterproof, airtight seals when it comes to electronics, construction, or in the automotive applications. Number 5 is the flexibility and dampening. So adhesives like silicones maintain elasticity, which absorbs shocks and vibrations. This is very helpful when it comes to electronic assemblies, vehicles, and even medical devices where protection from constant movement is required. Number 7 is the cosmetic structural integrity. So adhesive bonding leaves no visible hardware, unlike bolts or welds. This enables cleaner aesthetics, especially important in consumer electronics, appliances, and luxury vehicles. It's also useful for fragile or small parts that may be damaged by traditional fastening. Disadvantage to adhesive bonding. The first one is surface preparation. This requires proper cleaning, abrasion, and possibly priming. Improper prep can lead to bond failure, and what this basically means is any dust, oil, oxidation, or moisture can drastically weaken the adhesion used. Some surfaces may need to have abrasion or priming, and this will add time and skill requirements to the process. Number 2 is curing time. Some adhesives need hours or days to fully cure, which slows down the production compared to welding or mechanical joining. During this time, parts may need to be clamped or held in place, which can slow production lines. There are fast curing adhesives out there, but many compromise on strength or temperature resistance. Number 3 is limited load tolerance. It's not suitable for joints under tension, cleavage, or peel loads. Adhesive joints perform best under shear loading. This makes adhesives unsuitable for many structural or load-bearing applications without any additional design considerations. Number 4 is environmental sensitivity. Some adhesives degrade under UV exposure, high heat, or moisture unless specially formulated. For example, acrylics are excellent for UV resistance. In applications like outdoor construction or aerospace, specialized adhesives are needed to prevent breakdown over time. Number 5 is difficulty disassembly. So basically, bonded parts are often permanent or require destructive removal. So disassembling often damages one or both parts, which will limit the ability to repair or recycle them. It's not ideal for applications where maintenance, part replacement, or disassembly is super important. Number 6 is shelf life and storage conditions. Adhesives have limited shelf life or require specific storage, temperature, and humidity. So they can expire and lose effectiveness over time, especially if not stored properly, and many require specific humidity and temperature control, which adds logistics costs to it. Some are two-part systems with limited pot life once mixed. Number 7 is skill and consistency. Precise application and pressure are necessary. Automated systems help, but in manual or field repairs, worker skill becomes a major factor in quality, and is not as straightforward as a bolt or weld if rushed or performed without proper training.
Finally, soldering, brazing, and adhesive bonding. Each one offers unique advantages and disadvantages tailored to specific applications. The choice of joining method depends on the specific requirements of the project that you are dealing with, including material types, strength needs, and environmental conditions. Soldering is a perfect use for the ones that you need for electrical connections or conductivity, since you are using a metal also for combining both or as many components as you need. Brazing provides strong joints with high temperature. And finally, adhesive bonding offers the ability of joining dissimilar materials,